Hello students, in this video I will discuss valence bond theory to explain formation of covalent bond. Covalent bond is formed by the sharing of electrons between two atoms. Let us understand formation of hydrogen molecule by two hydrogen atoms, hydrogen atom A and hydrogen atom B. When these two atoms approaches to each other, then electron of each atom experiences two types of forces. First is attractive force from other nucleus and second one is repulsive force from each other. As electrons are negatively charged, so they repel to each other. This theory suggests that initially force of attraction is more as compared to force of repulsion, and hence atoms approaches to each other gradually, and at a particular distance this attractive force counterbalances the repulsive force, and at this time the energy of this system is minimum, and this is the condition when atoms are said to be bonded with each other and they make molecule. If further this distance decreases between the atoms, then energy starts increasing, or we can say that repulsive force becomes more stronger than attractive force. So in this way, this is the distance at which electrons of each atom feels maximum attractive force from nucleus of other atom, and hence this is the condition when atoms are said to be bonded with each other. This sharing is called as overlapping, means when these electrons feels attractive force from others nucleus, then this condition is said to be the overlapping of atomic orbitals, as electron remains in orbital in an atom. Bond is said to be formed in between two atoms when orbitals overlap with each other symmetrically, means it is a positive overlap or in phase overlap. Positive overlaps with positive lobe, okay, py py and pz pz, s and p can overlap like this. So in this way, depending upon the direction of overlapping, bonds are of two types. First is sigma bond and second is pi bond. Sigma bond is formed when two atomic orbitals overlap and the overlapping area lies on internuclear axis. It is also called as head-on overlapping. This sigma bond is formed by the overlapping of ss orbitals or sp orbitals or pp orbital, or we can say that px px orbital. As it is clear from this diagram that ss overlapping gives sigma bond as overlapping area lies on internuclear axis. SPX overlapping also gives sigma bond because overlapping area lies on internuclear axis, and similarly in case of PX-PX orbital overlapping, this overlapping area lies on internuclear axis. Second type of bond is pi bond. This bond is formed when orbital overlapping takes place vertically, or it is called as sidewise overlapping, as is clearly seen in this diagram. In this overlapping, the overlapping area lies away from internuclear axis. This is internuclear axis, okay, and overlapping area lies just above the plane and below the plane, so it doesn't lie on internuclear axis. Since sigma bond is formed when overlapping area lies on internuclear axis, so sigma bond is stronger as compared to pi bond. In pi bond, total electron density divides into two parts, so it becomes weaker as compared to sigma bond. Now let us understand that how this bond. During bond formation, always first sigma bond is formed and thereafter pi bond is formed if required. Now, to understand the geometry of many polyatomic molecules, we should understand the concept of hybridization because it helps to describe the geometry of molecules. This theory was developed by Pauling, and according to him, the atomic orbitals combine to form a new set of equivalent orbitals, and these orbitals are known as hybrid orbitals. Unlike pure orbitals, the hybrid orbitals are used in bond formation, and this phenomena of intermixing of orbitals is called as hybridization. Hybridization can be defined as the process of intermixing of the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shape. For example, when 1 2s and 3 2p orbitals of carbon hybridize, there is a formation of 4 new sp3 hybrid. Let us understand sp3 hybridization. sp3 hybridization means one s orbital when combined with all the 3p orbitals, then it gives 4 hybrid orbitals. Let us discuss formation of CH4 molecule. In CH4, carbon is central atom. Okay. Now its ground state configuration is 1s2, 2s2 and 2p2. In excited state, one of 2s electron will go to 2p subshell. So in this way, excited state configuration of carbon atom becomes 1s2, 2s1 and 2p3, and it can be shown by this block diagram. Now after that, all these orbitals which are singly occupied, 2s1 and 2p3, all these 4 orbitals combine with each other and they make 4 orbitals which are of the same energy, and these orbitals are called as hybrid orbitals. Now these 4 hybrid orbitals orient around carbon atom in this way that they feel minimum repulsive force, and this arrangement is called as tetrahedral arrangement. Now after that, all these 4 orbitals overlap with 1s orbitals of hydrogen atom, and in this way we get tetrahedral structure of methane, in which bond angle is equals to 109 degree or 109.5 degree. Now let us understand hybridization in ammonia molecule. In ammonia, nitrogen is central atom and its configuration, ground state configuration is 1s2, 1s2, 2s2, 2p3. All the p orbitals are singly occupied, px1, py1 and pz1. This is its excited state configuration also, means s orbital contain 2 electrons and all the 3p orbitals contain 1 electron. After this, all these 4 orbitals overlap with each other as we have discussed for methane, and we get 4 hybrid orbitals of same energy. Now in this case, one hybrid orbital contains 2 electrons. Okay, we can show these hybrid orbitals like this. After hybridization, we get 4 hybrid orbitals. First hybrid orbital contains 2 electrons and all the 3 remaining hybrid orbitals contain 1 electron. So these 3 hybrid orbitals are overlapped by 1 hydrogen atom, and we get a structure of ammonia. Now interestingly, in this case the bond angle is not 109.5 degree but it is 107 degree. Now valence bond theory could not explain that why in ammonia bond angle is 107 degree and why in methane is 109.5 degree. although both molecules have same type of hybridization at their central atom. So to explain this difference, one theory was given, and that theory is known as valence shell electron pair repulsion theory. Okay? This valence shell electron pair repulsion theory is also known as VSEPR theory, and it gave very important points to describe geometry of molecules. According to this theory, the shape of a molecule depends upon the number of valence shell electron pairs, that is bonded or non-bonded, around the central atom. Pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. It is very important. Third, these pairs of electrons tend to occupy such positions in space that minimize repulsion and thus maximize distance between them. When electron clouds repel to each other, they move away from each other and acquire that position in space where they feel minimum repulsive force, and in this case molecule becomes stable. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. So with the help of these points of valence shell electron pair repulsion theory, let us understand the why bond angle in ammonia is 107. According to this theory, as we have discussed, every electron pair repel to each other, and repulsion between lone pair and bond pair is more as compared to repulsion between bond pair and bond pair. These electrons are bond pairs, bond pair, bond pair, as these are making bond, and this electron pair is called as lone pair, as it is written over here LP. So according to valence shell electron pair repulsion theory, repulsion between LP and BP, BP bond pair, so repulsion between LP BP is more than repulsion between BP and BP, bond pair and bond pair. So in this way, these orbitals come closer to each other, these three orbitals, and hence bond angle becomes 107, which was 109.5 degree in methane. Okay. In the same way, we can understand molecular shape and bond angle in water molecule. Water molecule, central atom is oxygen. Configuration of oxygen in ground state is 1s2 2s2 2p4. In block diagram, we can show its configuration like this. This configuration is same for ground state and excited state. And after that, all the four atomic orbitals, these 2s2 and 2p4, combine with each other, hybridize, and we get four hybrid orbitals of same energy, in which two hybrid orbitals contain 2 electrons and two hybrid orbitals contain 1 electron. So the orbitals which contain single electron, these orbitals overlap with hydrogen atoms and make two covalent bonds. Now two lone pairs are present at oxygen. So these two lone pairs repel to each other. So repulsion between LP-LP is more than LP-BP, and repulsion between BP-BP is least. So in this way, these hybrid orbitals come closer to each other, and hence in water molecule the bond angle further decreases and it becomes 104.5 degree. Okay. Now second hybridization is sp2 hybridization. In this hybridization, there is the involvement of one s and 2 out of 3p orbitals in order to form 3 equivalent sp2 hybridized orbitals. Let us take the example of BCl3 molecule. In BCl3 molecule, boron is the central atom. So let us discuss its hybridization. Now ground state configuration of boron atom is 1s2, 2s2, 2p1. In excited state, one of s electron will go to p subshell, and in this way its excited state configuration becomes 1s2, 2s1, 2p2. Now after that, these 3 orbitals undergo hybridization and we get 3 hybrid orbitals. To feel minimum repulsion, these 3 hybrid orbitals orient around boron atom at an angle of 120 degree, and these hybrid orbitals after that overlap with unoccupied p orbital of chlorine and we get 3 sigma bonds. Since bond angle between bonds is 120 degree, so shape of BCl3 molecule is trigonal. Now next hybridization is sp hybridization. This is the hybridization in which one s and one p orbital undergo hybridization process and they produce 2 hybrid orbitals. Let us understand this by taking example of BeCl2 molecule, beryllium chloride. In this molecule, beryllium is the central atom. The ground state configuration of beryllium is 1s2, 2s2 and 2p0. In excited state, one of s electron, 2s electron will go to 2p subshell, and in this way its configuration, excited state configuration becomes 1s2, 2s1 and 2p1. After that, these 2 orbitals intermix with each other, undergo hybridization process and produce 2 hybrid orbitals of the same energy. Now these hybrid orbitals after that overlap with p orbitals of chlorine atom and a linear structure or linear shape molecule is formed. Now let us discuss some other examples of sp2 hybridization. sp2 hybridization in C2H4 molecule or ethene molecule. In C2H4, carbon is the central atom. Okay, 2 carbon atoms are bonded with 4 hydrogen atoms, 2 hydrogen atom with each carbon atom. So in this way, carbon atom is the central atom of this molecule. Ground state configuration of carbon atom is 1s2, 2s2, 2p2. In excited state, one of the s electron will go to 2p orbital, and in this way excited state configuration becomes 1s2, 2s1, 2p3. Now after that, 1s and 2p orbitals out of 3 combine to give 3 hybrid orbitals. These hybrid orbitals are known as sp2 hybrid orbitals. Okay. Now this third p orbital remains unhybridized. These 3 hybrid orbitals orient at the angle of 120 degree to each other, and these 3 hybrid orbitals overlap with hydrogen atom, 1s orbital of hydrogen atom, and 2 hybrid orbitals, 1 hybrid orbital of both carbon atom, they overlap with each other axially and a sigma bond is formed. During this overlapping, unhybrid p orbital also overlap with each other sidewise and a pi bond is formed along with a sigma bond. Okay. So this is the structure of ethene molecule where bond angle is 120 degree. 1 pi bond is formed between 2 carbon atoms along with 1 sigma bond. Next, let us discuss sp hybridization in ethyne molecule. Again, in ethyne molecule, carbon atom is the central atom. Ground state configuration is 1s2, 2s2, 2p2. In excited state, one s electron will go to p subshell, and hence excited state configuration becomes as 2s1 2p3. Now after that, only one s orbital and only one p orbital undergo hybridization process, and these orient at the angle of 180 degree to each other. Now two p orbitals remains unhybridized. So during this sigma bond formation between carbon-carbon and carbon-hydrogen, both unhybrid orbitals overlap with each other to give pi, and in this way we get two pi bonds along with sigma bond between carbon atoms. So the geometry of ethyne molecule is linear since hybrid orbitals are oriented at the angle of 180 degree to each other. Let us discuss some other molecules with some other hybridization processes. First, PCl5 molecule. In PCl5, phosphorus is the central atom and its ground state configuration is, valence shell configuration is 3s2 3p3. In excited state, one of the 3s electron will go to 3d subshell, and hence excited state configuration becomes as 3s1 3p3 3d1. After that, all these 5 orbitals combine and undergo hybridization process, and we get 5 sp3d hybrid orbitals. Okay, so these hybrid orbitals are called as sp3d hybrid orbitals. These orbitals are of same energy, and every orbital is occupied by 1 electron. Now these 5 orbitals orient around the nucleus of phosphorus, and these are directed towards the 5 corners of a trigonal bipyramidal as shown in this diagram. These 5 orbitals overlap with singly occupied p orbital of chlorine atom, thereby giving 5 covalent bonds. Bond angle of these 5 bonds are not equivalent. 3 PCl bonds lie in one plane at the angle of 120 degree, and these are called as equatorial bonds. 2 PCl bonds are perpendicular to this plane. One lie above the plane, one lie below the plane at the angle of 90 degree, and these bonds are called as axial bonds. These axial bonds feel more repulsive force as compared to equatorial bonds, and hence these are weaker than equatorial bonds. Next molecule is SF6 molecule. In SF6, sulfur is central atom. So let us discuss hybridization at sulfur atom. Now valence shell configuration of sulfur atom is 3s2 3p4 3d0. In excited state, one of s electron and one of p electron will go to d subshell, thereby giving configuration 3s1 3p3 and 3d2. After that, all these 6 orbitals, 1s, all the 3p and 2d orbitals combine with each other. sp3d2 type hybridization takes place, and in this way we get 6 hybrid orbitals of same energy. These 6 hybrid orbitals orient around nucleus of sulfur, and these orbitals are directed towards corners of a octahedron, and this is shown in this diagram. All these 6 orbitals overlap with 6 fluorine atoms, thereby giving 6 covalent bonds. These are situated at corners of octahedron, hence the geometry of SF6 molecule is octahedral, and each bond angle is 90 degree. Now this is all about molecules and different type of hybridization. Now this table gives an idea about type of hybridization and shape of the molecule or ions associated with that. For example, DsP2 hybridization is associated with a square planar shape, sp3d associated with trigonal bipyramidal, sp3d2 in some cases associated with square pyramidal, and in some cases it is associated with octahedral. Octahedral shape is also associated with D2sp3 hybridization. So this is all about this video. In this video I have discussed valence bond theory and shape of molecules. Now, although valence bond theory explained in detail about shape of molecules, but still it could not explain about magnetic properties of compounds. So, for that another theory was developed, which is known as molecular orbital theory. In my next video, I will discuss about this molecular orbital theory in detail. Thank you.